to today's session on Azure Global Load Balancer. Yes, load balancers are not specific to region related workloads, but now it has been in GA or generally available for people to utilize it to share traffic between the regions or cross region load balancer. Yes, it is also known as cross region load balancer. So, in this video, we are going to explore global load balancer or Azure cross region load balancer. So, as the name says, this is what it's gonna do, and we will try to understand with the help of our diagram, right? So, let's suppose these are our load balancers. Why these? Because they must be backend for the global, right? And then we have virtual machines at the backend. These are the virtual machines at the backend. All right. So once I'll start naming them, you would have the understanding what I'm trying to do. So this is your Azure tenant, maybe. Okay, because you are creating your resources in your tenant. So this is your Entra ID tenant, Entra tenant. Okay, this is your let me call it GLB as a global load balancer. This is your Azure load balancer, the standard Azure load balancer, which is regional. Okay, and these are the VMs which will act as a backend for your regional load balancer or ALB here. Okay, we have already learned the ALB. Okay, the various aspects of ALB, but today it's all about GLB, which is global load balancer. Now this global load balancer also works on layer 4. Okay, and the global load balancers that we have, the other ones like front door and traffic manager. Front door works on layer 7, traffic on DNS, right? So this load balancer works on layer 4 and send the traffic to their backend. What are the backends here? As you can see, the backend is Azure Load Balancer. We'll keep exploring it and you'll find it really interesting how things unfold. Okay. This is again layer 4 load balancing solution designed to distribute incoming traffic across multiple Azure regions. Okay. This is really important. So let me call it region 1. Let me call this as a region 2. That's what it makes it cross region. Region 1 and region 2. Right. Now this load balancer, how this load balancer becomes global load balancer, because there is a public IP attached to it. Okay. And this public IP does the magic. Why? Because this is anycast IP, public IP, and it is advertised in all the global locations of Azure. Okay, so it ensures geo redundancy. As you can see, region, you can have multiple regions, right? So it ensures geo redundancy. Okay, high availability because multiple regions, one is down, it will send it to the another region, and optimal performance. Okay, and seamless failover capabilities. All this is possible because of anycast public IP address. Okay, so if you have to define what is Azure Global Load Balancer or Azure Cross Region Load Balancer, you can simply define it as it's a Load balancer, it's a global or cross region load balancer, works on layer 4 load balancing solution designed to distribute incoming traffic incoming traffic across multiple Azure regions. Okay, and it ensures geo-redundancy, high availability, optimal performance, and seamless capabilities. Now, as you can see from the architectural perspective, there are like few architectural components, just like the other load balancers or standard load balancers that we have learned as of now. The very first is the public IP. This is a front end IP. So this utilizes a static anycast public IP address, ensuring consistent and reliable connectivity for clients worldwide. Okay. Second, the backend pools. The backend pools consist of multiple regional standard load balancer, each managing traffic within respective Azure regions. And this setup allows for efficient distribution and failover mechanism. Now, it's very simple because there must be health probes so that this knows where to send the traffic and the load balancing rules, right? So these are few components, but the interesting fact is this anycast. Okay, so let's explore this anycast a little further. So Azure Global Load Balancer uses anycast public IP, which means it needs to route traffic to another public load balancer. Okay, so this load balancer, which is at the back end of the Azure Global Load Balancer, is a public Azure Load Balancer, not the internal one. Why? Because Anycast can only send to the public IP. That's why. So, point to be noted, only the public load balancer could be the back end of the global Azure Load Balancer. Now, internal load balancer do not have public IP, so it cannot be there. So what it means? Well, for example, if you want global load balancing for an application that should not be directly exposed to the internet, okay, in that situation, how could you make it global? Well, there is a workaround. We can simply use external load balancer while keeping the actual application behind the private load balancer. So public load balancer will act as an intermediary to forward traffic to an internal load balancer. There must be another load balancer here. So it would be like this. The point is backend could be public, but if you want to send to the internal, then you still need to use public, and it will act as an intermediary and send the traffic to internal load balancer and then distribute the traffic. This is an important point I wanted to make. Now we need to check anycast further. The very first point is it will send to the public IP. Now, uh, this anycast, this gets advertised globally. Okay, so anycast IP is a networking technique where a single IP address is advertised to the multiple locations across the global network. Now, Azure uses Anycast IP to provide low latency, high availability service by routing users' traffic to the closest available endpoint. Okay, so it will be more like this is tenant, this is region, and everything. So you could say there are multiple edge locations, right? When Anycast IP is advertised in Azure, the traffic enters Azure Global Backbone Network as soon as it reaches the closest edge location. Okay, so there must in every region there are multiple edge locations that we have seen in our express route as well. So all this public IP is already advertised in the various edge locations. So let me try here. Let's suppose this is the Microsoft Backbone Network and there are multiple edge locations, okay, in every region like this. Let's suppose there are two edge locations here and there are two edge locations here. So this public IP which we have right here will also get advertised, in all the edge locations, right? Here we have this IP, here we have this IP, here, and we have this IP here. All right. Now, when a user sitting somewhere try to access this public IP or xyz.com something over the internet, okay, there is DNS, okay, public DNS somewhere, DNS. Now the user types xyz.com, it will go here, then it will return back, and the ISP will take care to the nearest public IP address, and it will get into the Microsoft backbone and reach. Okay, that's how it will work. Now, when a user requests xyz.com, as I said, the DNS resolves the domain at an anycast public IP address, right? xyz.com. It will send the this public IP address, uh, anycast public IP address. Now from here, the user's ISP will take over. ISP routes the request towards the Azure. Okay. Now Azure advertises the Anycast IP from multiple edge locations globally, as we have discussed. The ISP network decides which edge location is closest based upon the BJP path selection, BGP path selection, or shortest latency and peering agreements, traffic load balancing policy. So there are multiple ways, right? And ISP chooses the shortest available BGP path to an Azure POP if there are multiple POPs in a region. If latency is high at one POP or POP, traffic may be rerouted to another POP. Okay. Azure has a direct peering agreements with major ISPs to ensure traffic is routed optimally to the POPs. So this is already been taken care of. You need not to worry about it. I'm just trying to explain so that you would have a clear picture in your mind when you think how exactly the traffic is happening. All right, so that's how it makes it geo-redundant, highly optimal, low latency, and highly available. All those features that comes with the Anycast, just like with the front door. Yes. Now you'll find interesting because this is globally advertised. So now it eliminates the need for multiple DNS-based endpoint management and also reduces latency and ensure fast failover without waiting for the DNS TTL updates. Request come here or it will go there. No need to wait for that, right? And it is another thing is it supports all those things that the standard load balancers were doing earlier because it works on TCP and UDP. So supports any TCP or UDP based application, not just web traffic, and it is ideal for VoIP, database replication, multiplayer gaming, remote desktop. So if you have any such application or requirement, global Azure Load Balancer is your choice. Why? Because there are other global load balancer like front door or traffic manager is there. When you need to choose GLB, well, when you have the applications like this, when you do not have web traffic with the requirement of WAF and other aspect that traffic manager provides, it is always good to have a global load balancer for those applications like VoIP, database replication, and multiplayer gaming, right? Any TCP UDP traffic. And the best part is the user who is accessing this IP will be reserved. Yes, this preserves the client IP for security and logging. This IP will be preserved. Unlike Azure Front Door, Global Load Balancer preserves this client IP and helps backend services apply security rules based on the client's real IP. And it is also essential for security policies, compliance, and analytics. Now, There is built-in health probes for intelligent traffic routing. So automatically detects failures in Azure regions and reroutes traffic to the next available region. That is a GLB's feature. And it is cost effective as compared to any global load balancer like cro- like front door or any other. The Azure global load balancer across region load balancer is cost effective because it is cheaper than front door for non HTTP workloads and does not rely on expensive DNS based failovers like traffic manager, right? And let's summarize this point. When we need to choose Azure global load balancer, when the requirement is low latency, high performance TCP UDP balancing, low latency, high performance on TCP UDP based workloads. When we need real time failover, right? And no need to wait for the TTL DNS and all that we have already talked about. And whenever we need to preserve the client IP, and whenever we are handling non HTTP workloads, it can handle that as well, but usually those workloads require other security aspect like layer 7 handling where we have the SSL or WAF. So in that situation, the workloads like database replication and VoIP or gaming, you can utilize this one, which would be highly performant, right? And if your application needs network level resiliency rather than layer 7 application processing, right? Network level resiliency over over L7 app processing. Any aspect of L7 processing, as we have mentioned, like SSL and WAF and other stuff, right? So we have to choose this load balancer. It also support those things that we were talking about in our standard load balancer, so not digging there around, because before two videos we talked about that, like HF ports or floating IPs. It supports all that. And apart from this, I think we have already covered the global load balancer. There are certain things, the anycast and the public load balancer, regional. Yeah, I think that's all about the Azure global load balancer. And I hope it was informative. And thank you for watching. You guys have a wonderful day.